You've decided to share code between Node.js and the browser. Great. Now here's the problem: some of your code needs to behave differently depending on where it runs. In the browser, you use the Fetch API to make HTTP requests. In Node.js, you use the built-in HTTP module or a library like Axios. The logic is the same. The implementation is different. The naive solution is to check at runtime which environment you're in. You've probably seen this: type off window == undefined. If that's true, you're in a browser. If it's false, you're in Node.js. Or the inverse, checking for process.browser, or checking if process and process.versions.node exist. This is called runtime code branching, and it works. But it has a subtle cost that becomes significant at scale. When you use webpack to bundle your code for the browser, webpack includes both branches, the Node.js path and the browser path, in the bundle, even though only one will ever run. The Node.js specific code is dead weight. It inflates your bundle size. Users download code that will never execute. For a single conditional, this might be a few hundred bytes. But if your shared codebase is large and has dozens of these platform checks spread across utility modules, the dead code accumulates. Bundle size directly affects initial page load time, which directly affects user retention. Google's research showed that a 1-second delay in mobile load times can reduce conversion rates by up to 20%. So the goal isn't just make the code run, it's make the code run without paying unnecessary costs. That's what drives the more sophisticated techniques we'll cover: build time branching and module swapping. Here's a better approach than checking type-off window at runtime: eliminate the wrong platform's code entirely before the bundle is even created. This is build-time code branching, and Webpack makes it possible through a plugin called Define Plugin. Define Plugin does a global search and replace across all your source code at build time. You tell it to replace every occurrence of process.env.platform with the string literal browser, and it does. Literally. Before any bundling happens, every place in your code that says process.env.platform now says browser. Now when Webpack's tree shaker analyzes the bundle, it sees conditionals like, if, browser == node. That condition can never be true. The tree shaker recognizes it as dead code and removes it entirely. The Node.js code path never makes it into the browser bundle. This is how React works. In the production build of React, if you open the minified source, you'll see that all the development mode warnings are completely absent. They were gated behind if process.env.node_env == production checks, and Define Plugin replaced process.env.node_env with production before bundling. Result: React's production bundle is significantly smaller than the development bundle. The minified production build of React DOM is around 42 kilobytes, while the development build is around 126 kilobytes. The pattern is, write your platform checks using named constants that Define Plugin knows about, not dynamic runtime checks. The code reads the same during development. The dead code is eliminated in production bundles. Zero cost at runtime, zero code in the wrong environment's bundle. Sometimes an entire module needs to be replaced with a different implementation per platform. Not a single conditional, the whole file is different. You want one file loaded in Node.js and a completely different file loaded in the browser. Webpack's resolve.alias configuration is built exactly for this. The pattern works like this: you have a module that your application imports normally, let's say it's called request.js and it's a thin wrapper around HTTP requests. You write two implementations, request.node.js which uses Node's built-in HTTP module, and request.browser.js which uses the browser's fetch API. Both files export the same interface, same function name, same parameters, same return type. They're drop-in replacements for each other. In Webpack's config, you add an alias. Whenever Webpack sees a require for request, it resolves it to request.browser.js instead. On the server, Node.js loads the file directly with CommonJS, so it gets request.node.js. In the browser bundle, Webpack's alias kicks in and the browser version is bundled. This pattern is known as module swapping, and it's the basis of how many cross-platform libraries handle their platform-specific implementations. If you've used React Native, this is exactly how its module resolution works. .ios.js and .android.js files are the platform-specific implementations that get swapped in based on the target platform. The deeper design pattern here is the strategy pattern applied at the module level. Your consuming code doesn't know or care which implementation it gets. It calls the same interface. The bundler makes the decision about which implementation to provide, based on the build target. Separation of concerns enforced at the build level. Let's step back and look at the three techniques we've covered as a coherent design philosophy, because the choice between them matters more than any single implementation detail. Runtime code branching, the type-off window check, is the simplest approach and appropriate for small, infrequent differences. It has the advantage of working without any build tool configuration. The cost is dead code in your bundles. Use it sparingly, for one-off checks where the platform difference is minor. Build time code branching with define plugin is the right choice when you have conditions scattered throughout a module that differ by environment. The dead code gets eliminated, bundle size stays lean, and the source code remains readable. The trade-off, it requires a webpack build step and the right define plugin configuration. This is the standard approach for large codebases and is what React, Vue, and Angular all use internally. Module swapping with resolve.alias is for when an entire module has fundamentally different implementations per platform. It keeps platform-specific code completely separate, different files, different directories. The consuming code is completely unaware of which implementation it receives. This is the cleanest separation, but it requires discipline. Both implementations must maintain identical interfaces. What ties all three together is a single principle: your universal business logic should be completely ignorant of which platform it runs on. The platform-specific wiring happens at the edges either via runtime checks, build time elimination, or bundler-level substitution. Get this separation right, and you can test your business logic once in Node.js with fast unit tests, bundle it for the browser, and be confident it works the same way in both environments. That's the promise of universal JavaScript, not magic, but disciplined separation.